So are you ready? Listen. Yes, I wanted to let you hear me clear my throat. This is it. This is the last week. We are covering both chapters 11 and 12 because frankly 11 and 12 cover the same thing. 12 is just kind of a little extension of 11. Nothing new. It's a good thing this is our last week. We've been together for 8 weeks and things are falling apart. You'll notice that the camera is a little bit tilted. Well, that's because my pathetic little camera stand is falling apart. It has not held up well because it's a piece of garbage. That's all there's to it. Couldn't get my fruit pie this morning. Usually I buy fruit pie to eat for sustenance while I'm putting together these videos. I don't want to hear it. Fruit is healthy. Fruit is health food. It's good for you. Fruit pie is made of fruits, therefore fruit pie is health food. Alright. I hope you've learned something. I've learned that I bought a cheap-ass little stand for my video camera. It's falling apart. Pretty sad if you ask me. I've had a lot of fun. I'm glad that I've had the opportunity to use this video camera. I bought it basically for a wedding. See, look at that, it's falling apart. I bought it for a wedding. This young couple wanted me to do their wedding video for them, and they did not have a camera to film it, to record it. God, that's pathetic. So I recorded it. I bought this just for them so I could record their wedding, and it has not been used since. So I've used it every time I've made love to a woman, and I've had it for 3 years, and I used it only for their wedding. So I'm glad that we have another excuse to use this kind of expensive little toy that otherwise would never be used. Should have bought a better stand. You feel like you're on the ocean? I'm gonna do this all day long. I'm gonna do who is that? That blind singer that used to do that all the time. Stevie Wonder. I'm gonna do Stevie Wonder all day. I'm just gonna do this. See if I can't make you seasick throughout the entire lecture. All right. Chapters 11 and 12 are a little odd. We're working with complex numbers, which we started to learn last time. I'm going to go about it a little differently. If you recall, in the book, they defined J to be equal to the square root of -1. I have always learned it as I. I've seen some, it just depends on who's doing it. I think engineers like to use J. I tend to use I. Okay, I don't know what my camera's doing there. So remember, if I use I, the book uses J. It's the same thing, and it is not a variable. I is defined as square root of -1. It is imaginary. That's why I like I better. I, imaginary. It's not real. So the book begins by defining Z as a complex number. A complex number is a number that has both a real component, that's your x, and an imaginary component, which is I times y. Remember, any function that has a square root of -1 in it, we can just take that square root out. So what we're doing is the imaginary part actually is a multiplier between a real number y, or a real function y, depending on how you want to define it, and the square root of -1, which is I. So this is a complex number. Z is a complex number. It has a real component and an imaginary component. The imaginary component is I times another real component, but there's something else. The book uses a variable alpha. Alpha. Alpha is a Greek letter. It's the first letter of their alphabet. This is a lowercase alpha. There's a larger case alpha. But they don't actually use this. They use alpha equals. Well, alpha is just a multiplier. That's all it really is. So if you multiply this function by z, it means that we have to multiply both sides. I'm sorry, if we multiply this side by alpha, we have to multiply both sides by alpha. We're going to multiply x plus I of y times alpha, which gives us, if we multiply it out, how does the book do it? Sorry. Which is this. Now the book starts pulling fast ones. They don't really explain it well. They just kind of give you definitions. They give you the Cartesian form of alpha times z, and all of a sudden they just give you, oh, now here's the polar coordinate version. The exponential form, I'm sorry, the exponential form. And they don't really explain where that comes from. The exponential form comes from Euler's equation in chapter 10. Where Euler's formula, said let cosine theta plus sine theta equal r e. Oops, I'm sorry, there's an imaginary component here. Let the complex number sine theta plus I times sine theta equals r e to the I theta. That's Euler's formula, and we talked about that and some of its applications. Well, I would like you to remember, well, I don't want you to remember, so if we let x equals cosine theta and y equals sine theta, and what we have here alpha z, which is our complex function or complex number, is alpha times cosine theta plus I times alpha, times alpha times I sine theta. Cosine theta plus I sine theta is, and this is what the book gives you. Dagnabbit. See, I couldn't get my fruit pie today, so I'm not thinking straight. Crap on a popsicle stick. There we go. This is where this comes from. They took they took alpha out. They got cosine plus I sine theta, the quantity times alpha. Cosine theta times I sine theta is r I theta. So alpha z is equal to alpha r e to the I theta. Shit. Enough of that. And what they did was they called this one the Cartesian form. And they called this one the exponential form. The problem is, what they are doing here is not purely mathematical. They have defined these values for application purposes, and we are going to talk about some of these applications. But basically, it's because of certain applications that they are giving you these two forms. These are only equivalent if this is true. this is true, then this is true. And the reality is, this can only be true if x and y are between -1 and 1. So if you have some function where x equals 14, this is impossible. I'm sorry, maybe it's not. I'm sorry, I'm wrong. Because this is impossible. But alpha times this can be 14. So if alpha times x, and that's, I guess that's the key. If you have 14, then alpha x equals 1, and 1 is possible with cosine. If alpha equals 14. But if cosine equals 1, sine does not equal 1. So you're going to get a different imaginary term here for the same function. Now, this is limited application. This is limited application. They don't tell you what those limits are. I'm looking at this, and it's just, there are limits. If we know theta, if we set theta to get the x that we want, y is going to be fixed for us. So our imaginary component is always going to be a function of the proper component, of the real component, or vice versa. We could, if we know what y we want, we could set theta so that y gives us what we want, but then x becomes fixed. So for one angle theta, this is not possible. This gets fixed. I don't know, maybe I'm wrong. But it's not really critical. What I do want to do, though, is work through one problem with you because it's wrong. It's wrong, it's wrong, it's wrong. On page 116, that's this many. It's that many. On that page, sorry. I had a marvelous birthday party last week with a young lady who just turned 6, and not just her, but her and her mother. I don't date 6-year-olds much, so anyway, they invited me to dinner with them. We had a lovely dinner, and she's this many. So anyway. And by the way, we went to a sushi restaurant, actually a Japanese grill, and we sat with a young man and his family, and he was celebrating his 11th birthday, so it was kind of cool. I had the boy on one side, and I had the girl on the other, and I was just sort of playing with both of them. It was kind of fun. Anyway, on page 116, example 1 is wrong. Is wrong, is wrong, is wrong. Here's what they said. I'm going to keep these up here. I get the feeling those are going to be good references. What I put over here was just sort of showing you how they got the Cartesian form and the exponential form. Well, they said, suppose, I'm going to do this in a very different way. Very different way. No, I'm not. I can't. Here's the problem. They said, let z equals 1 over the square root of 2 plus, what did they do? Yeah, they put j first. Well, I don't use j, I use I. They said, here's your function for z. What they did was they defined x and y to be exactly the same value, 1 over the square root of 2. Then they said solve for alpha equals 2. Well, this z, here's alpha. Alpha times z is simply alpha times x times alpha times I times y. Well, we know x, so if we do this, alpha z then is going to be just substitute. It's alpha times 1 over the square root of 2, or alpha over 2. If alpha equals 2, we get 2 over the square root of 2, plus I times 2 over the square root of 2. That being the case, 2 divided by the square root of 2, I want you to prove this. Here's how you're going to do it. I'm not going to solve this for you. But 2 is 2 to the first power. Square root of 2 is 2 to what power? You should know this by now. Remember, if you're dividing by a root, the power of a root is raised to the fraction of that root. So, square root of 2, I'll write it down. Square root of 2 is 2 to the 1/2 power. So you have 2 over 2 to the first power. 2 to the first power over 2 to the half power. Remember, if you're dividing by powers, you subtract. So it's going to be 1 minus 1/2. So we're going to get 2 to the first over 2 to the 1/2. 1 minus 1/2 is 2 to the 1/2. 2 to the 1/2 gives us our final solution of 2 root 2 plus I times root 2. The book forgot the square root. The book has this solution as 2 plus I times 2, and that is incorrect. That is an error. Which really makes alpha in our final solution, if you think about it. Well, okay, we'll leave that as it is. By the way, something else I want to point out. The book does something a little bit weird. I wrote alpha z is equal to alpha r times e to the I theta. The book does something weird. The book, I forgot to mention this earlier, the book does this in the exponential form. They give you two possible solutions. This, by the way, is common mathematical formulation. This is very common for them. Alpha z has one of two possible equations. The one that I gave, if alpha is greater than or equal to 0. In other words, as long as alpha is greater than 1, as long as alpha is positive, alpha greater than or equal to 0, as long as alpha is positive, you use this form. Otherwise, if alpha is less than 0, we get e to the I theta plus pi. They never explain this. It's because there is no explanation. They're giving this as a definition. If you recall, if you have r and theta, you can plot that point as a function of distance r and angle theta. And this theta should be able to be 360 degrees. But if you have a negative number, which actually would put you down on this side, they're going to add pi to it. Remember, 360 degrees is 2 pi. Radians, 2 pi radians. And that's what they're doing here. So if you have a negative value for alpha, they're forcing it to be positive. They're adding alpha to it, which means that you can only go this side of the equation. Why would they do that? I have no clue. That's just a definition. make number 2. I'm going to put you on pause. I'll be right back. Well, here I stand, broken-hearted. I tried to shit, but only farted. All right. So anyway, like I say, the book never explains this. It just kind of says, well, we're only going to use the positive, the top part of the graph. And you never explain that. I'm not too worried about it. I don't think you should worry about it either. Here is the important part of this chapter. Again, for you, unless you go on to do some pretty high energy applications like physics, like quantum mechanics, this is all quantum. You'll probably never need to know this, but it is important enough that I would like to define it. The complex conjugate. I want to point this out and make this very clear. What you're thinking, what you are thinking right now, is not what this means. You're thinking complex conjugal. That's when you're having really complicated sex. This is the complex conjugate, not conjugal, conjugate. Math, the complex conjugate. Stop it. Geez, you have a filthy mind. All right, what is the complex conjugate? And why does it matter? The complex conjugate is always denoted with a star. An asterisk, a star. Depending on if you want to use star or asterisk, it's actually technically an asterisk. The complex conjugate is always the negative value of the complex term. That's all it is. The function, whatever this is, in the function you change the sign for the imaginary, only the imaginary part of the function. So z star, instead of being x plus iy, is x minus iy. Or alpha times z star will be alpha x minus alpha iy. In the exponential form, there's no imaginary term down here, so we're not changing the sign. The only imaginary term is up here, and we are changing the sign up there. In my class, at this point in time, I would have everybody at the top of their lungs say, on the count of 3, so what? So here's what I want you to do. I'm going to count to 3. When I reach 3 at the top of your voice, I want you to say, so what? All right? So the complex conjugate is the negative value of the imaginary term. 1, 2, 3. Great question. Here's why that's so important. Let's do a couple of examples in the little board space I've left, which is fine because this is pretty much the last thing we're going to talk about. Suppose we have a really simple function. Let x and y equals 1. There's that book influence. Then our function z is 1 plus I. And if we square that, z times z what do we get? Well, Well, 1 times 1 is 1. 1 times I is I. We're going to get that twice. Plus I squared. I squared, if you recall, is equal to minus 1. So we're going to get 1 plus 2i plus I squared and we get an imaginary result. We multiply the complex conjugates. We're again going to get 1 minus 2i minus I squared two plus 2i. All right, but here's the important example. This, all I wanted to demonstrate is you take this function z times itself, and if you want to throw alpha in there, that's fine, it doesn't matter. You'll end up with alpha squared times 2i, or alpha squared times the quantity 2 plus 2i. Throw alpha in, it's fine. You can do this math, it's not that complicated. But here's what I want you to note. What is the function z, not times itself, but times its complex conjugate? That's 1 plus I times 1 minus I. Well, I'm going to multiply this all the way out. 1 times 1 is 1. 1 times minus I is minus I. I times 1 is positive I. Positive I times negative I will give us negative I squared. These two terms, negative I plus positive I, these go to 0. I squared is negative 1, so we get 1 minus a negative 1, or our answer is 2. Here's the key to this. If you multiply a function times its complex conjugate, you get a real solution. There's no imaginary component when you take a function times its complex conjugate. That's the importance of the complex conjugate. Actually, there is one more thing we're going to do. Now, suppose we use the exponential form. Z times z squared, I'm sorry, z times the complex conjugate z, we get r e to the I theta times r e to the negative I theta remember, well, this is just r times r, that's r squared. If you multiply two exponents of the same variable, e is the same variable, remember you add the exponents. I theta minus I theta. I theta minus I theta equals 0. E to the 0, any number to the 0 power is equal to 1. Not 0, this is a common mistake a lot of students make. Any number raised to the power of 0 is not 0, it's 1. Any number raised to a 0, 1. So your final answer here is r squared. And again, once again, is a real number. I want to show you to show you the reason, an important application for this. When we're doing, and we've talked about this before, in quantum mechanics, We cannot know things exactly. We talked about that last time, but we can approximate. And you end up with a function looks like this. Very simple looking formula, but actually it's so complicated it's only been solved exactly for one system. Nothing else. Everything else is an approximation. This is a Greek letter psi. P-S-I. It's a Greek letter. And it has the form something like this. Well, look, this is very similar to this. The only real difference is I threw in an extra constant. So let's just take that out. What the hell? We don't need that constant. It has a radial component. This is how far away two electrons are from each other. That's that R value that we talked about. And it has a spatial component, that theta. So where is it in 2 dimensions? Now, by the way, this is where in 3 dimensions we would have to add that. It's usually called phi. So one angle is how far it is along this plane. The next angle is how far along it is in this plane. We can get 3 dimensions. But if we're talking about 2 dimensions, we're talking how far apart and what's the angle between them. That gives us the spatial arrangement of the two. This psi is what we call a wave function. A wave function. And a wave function has no meaning. It cannot have a meaning. Damn it! This book is driving me crazy. Remember, that's an I. I accidentally put a J in there. The wave function has no meaning. How can it have a meaning? It's imaginary. It has an imaginary component. That is going to mess us up. We can't do that. So the wave function itself has no meaning. But we want to take this wave function and calculate an energy out of it. How can we do that if the wave function has no meaning? Here's how. Because the wave function itself may have no meaning. But the wave function times itself, the wave function squared, is related to, remember we talked about this last week, the probability of finding an electron. So mathematically, the probability of finding that electron is psi times itself, or psi squared. But here's the catch. Remember we did that up here? Z times itself will give us an imaginary number. We can't have an imaginary probability. It's meaningless. We need a real probability. So how do we do this? If we, oh, boy, I feel better now. Whew. Well, I tell you, all that pressure. Anyway, a wave function times its complex conjugate gives us a real number. The wave function, which is imaginary, times its complex conjugate, which is also imaginary, gives us a real number, which is the probability of finding that electron. This is why complex conjugates are important. Applications are real. The applications in high energy physics, whoever wrote this book must have been a physicist or maybe an engineer, because clearly, anyway. This is why complex conjugates matter. So, recap. A function that has a real and an imaginary component. The complex conjugate means you take the opposite sign of only the imaginary component And a function with an imaginary component times its complex conjugate will give you a real number. And there it is in a nutshell. And that's what matters today. One last thing. This is again something that the book doesn't explain. But once again, it is something that I think is not terribly critical, so I'm just going to point it out to you. But they're not clear. They're not clear. They were using that graph. Remember, in the graph, the y component of that graph, that's your imaginary part. So along the x-axis, you have your real number. Along the y-axis, you have your imaginary number. And if you were to draw, that point, here's your opposite. Here's your adjacent. Tangent of this angle theta, remember, is your opposite over your adjacent. Well, they did that, and they managed to come up with these two little formulas. I'm not going to walk through the proof because I don't think it really matters. It's just a graphical representation. So they gave you two little formulas, and basically I'm mentioning this because in a couple of the following examples, they use these little formulas as if they're givens. So I'm defining them for you as a given. I'm not going to prove it. But the book will assume that 1 plus I is the square root of 2e to the I pi over 4. Pi over 4 becomes theta. R is equal to square root of 2. Square root of 2 is easy. It's 1 and 1. 1 squared times 1 squared is 1. I'm sorry. This is from Pythagorean theorem. 1 squared plus 1 squared equals r squared. 1 squared is 1, so 1 plus 1 equals 2. R squared equals 2. R equals root 2. Theta is pi over 4. Blah, 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 blah. Anyway, so they give you this as a formula. The complex conjugate is this. So, towards the end of chapter 11 and into chapter 12, they're going to start using these formulas like a given. They come about from the use of the tangent, the definition of tangent. It looks a little different from what we used to. Instead of r, you're seeing a square root of 2. Instead of theta, you're seeing a pi over 4. But these, the book will use more or less as a given, so don't let that shock you when you see it. And that is it. I have just taught you everything that I know. I know nothing else. I'm an idiot. No, I'm not an idiot. This is not easy stuff, if you want to know the truth. This is fairly complicated. But that's it. I'm done. The rest of it is up to you. Not entirely. If you have questions, guess who is still around to answer them? All you have to do, send me a note on Facebook, send me an email, give me a call, Skype me, sext me to get my attention, and then pull me in with questions. You know, I've been fooled before, so that works. I'm not proud of it, but there it is. I hope you learned a couple things. This point, it's calculus from this point forward. If you really want to do calculus, talk to me when you're ready. We'll see if we want to go into calculus, but of course, what we're doing here is manipulations. Mathematicians don't even consider this to be math. But calculus is basically the math of movement, the math of motion. So once again, a lot of examples out of physics with electrons, we're talking about motion. We may not know where they are, where they're going, but we know that they're in motion. So calculus comes into play. No more fruit pie for me. I am depressed. I'm debating. I may come up with an epilogue for you, and if I do that, the reason for the epilogue is because I'm betting that people will watch the epilogue before they get to the remainder of the chapter. I'll bet you will all watch the epilogue video first. I'm just kind of curious to see if that's true. So I may make an epilogue. If I do, it'll be from my apartment, not from here. But I hope that you learned something. If you have questions, let me know. I am here for you anytime you need me. Thank you.